Let's talk about performance. Let's talk about the deep level of optimizations in Kubernetes clusters. Today, I don't know, maybe some of you already heard about the thing called NRI, but we are going to do some minor overview what it is about, how it works, and what kind of plugins are available, and what kind of use cases it tries to solve. Let's see if it will be useful for you. Let's see if it will raise more questions for us. All right, few words about us. Myself, Alexander, and my colleague Krisztian, we are working at Intel at the software part of it. We are working on Kubernetes and our CNCF projects. We are participating in many of the tags, individual projects as well. And NRI is one of the things what our team is doing. So NRI, what stands behind this acronym? It's Node Resource Interface. Generally, it's a thing, it's a common extension point for the runtimes, but in reality, it's kind of very efficient Swiss tool where you can modify how your cluster is behaving, how your container is behaving. Mostly for performance optimizations, but it might be something else. So, 30 seconds overview, or bird view overview. The project is not new. It started almost 5 years ago by one of the containerd maintainers who is working in Apple. He was saying, kubelet creating a container which I would like to tweak a bit. And he looked at what is available in ecosystem, and he said, everything what is available is not good enough, let me do something. And he did very hackish approach in the containerd code to enable it. We came a bit later. We said okay, well, let's do it as a proper API. Let's improve it. We help it with coordinating with CRI-O project to make it really common API between the two most common runtimes. And afterwards, it became the real standard between all of them. It's available both in containerd and in CRI in all recent versions. In the Kubernetes stack, it's plugged inside the runtime. So kubelet, when it creates the container, it sends the description to the runtime. Runtimes transform it to an internal state. And this is where the NRI gets this internal state, gets all the information about all the internal parameters, can modify it, get back to the runtime, and when it actually runs. So that's the 30 seconds overview how it is. But now let's go a bit more in details what is inside.
Okay, so what constitutes NRI really in practice? So basically, core NRI comes in 3 pieces. So there is a wire protocol and a low-level API. So this is a protobuf described protocol description with TTRPC bindings. So TTRPC is basically, you could say it's gRPC for resource-constrained devices. So that's what NRI uses to communicate between the runtime and the plugins. So this low-level protocol, basically it defines 3 things. So it defines a data model. So what kind of modifications basically a plugin can do to a container. So it defines an event model, so when those modifications can be applied to a container, and then it defines a low-level programming API, so how those modifications can be carried out in terms of the protocol. So this wire protocol anyway is it's such a thing that if you are writing or considering writing an NRI plugin, this is not something that you are going to directly encounter. It's a low-level API. What you are going to encounter is the plugin stub. In addition to that, we also have the runtime adaptation. So that's basically a client for the runtime. So that is what the containerd and CRI-O integration code is using to interact with NRI. And then we have the plugin stub as the 3rd piece. So that's the primary integration point for plugging in extra logic to the runtime. It provides also a sort of higher level convenience layer than this low level API to make it more usable, easier to use and approachable. And it also contains a big bunch of boilerplate code. So basically that kind of code which is required for a functional NRI plugin but is shared, it's common for all the plugins, so the boring details. So how does NRI work? So NRI plugins are standalone daemons. They are not linked into the runtime. Their life cycle is not tied to the runtime. They can come and go independently of the runtime. They can be restarted independently, started independently. They can crash independently and get restarted because of that. So because of this extra complications, in a way, NRI needs 2 extra protocol bits to cope with all of this. So basically a registration part and the initial synchronization part. So the registration is used for letting the runtime know that because the plugin's lifecycle is independent of the runtime, that when a new plugin shows up, the runtime needs to know about it. So basically this registration and handshake constitutes mostly of the plugin telling about itself and some parameters, so where it wants to hook itself into this potentially multiple chain of plugins. Then it gets some configuration data about the runtime and optionally some plugin-specific configuration. And at the end of this phase, it tells the runtime what events it might be interested in. So there are several NRI events and it might not want to receive all of those. Initial synchronization, because plugins can come and go at any point in the life cycle of the runtime. So it might be that by the time a plugin is around, the runtime has been up for maybe 5 seconds, but maybe 5 hours.
Sorry, I cannot hear anything.
Sorry.
Speak a bit louder.
Okay, sorry.
So no speakers, so speak louder.
So the synchronization is about synchronizing the runtime state, current runtime state, with the state of the plugin when the plugin starts up, because there is no guarantee that how long the runtime has been running, what kind of containers have come and go, and what is the current state of the runtime when the plugin shows up. So what is the essence of NRI? What can plugins actually do? They can make changes to containers. But since a container is almost immutable once it has been created, NRI has 2 types of changes that a plugin can make. So we have adjustments. These have access to most of the container parameters, and these are the changes that a plugin can request during the creation of a container, so the very initial phase. Actually, it is applied before the container is created, because once the container is created, most of these parameters are immutable. Then we have updates. These are the changes that the plugin can request at any time during the life cycle of the container, unless the container has been stopped but not removed yet. These are much more limited changes. Practically, they are limited to compute resources. So CPU, memory, and other parameters related to CPU and memory, like CPU pinning, memory pinning. So, life cycle events. So NRI defines a number of events that plugins can hook into, and these are directly reflecting the comparable events in the CRI protocol for pods and containers. But from the NRI point of view, these come in 2 types. So there are those to which a plugin can respond with changes, and there are those to which it cannot respond with changes. So the events where you can request changes are the container creation. So this is where you can request most of the changes and the biggest scope of changes. In addition to changing the container being created, you can also request updates to all other existing containers. The other event, or another event where you can request changes, is when a container is being stopped. For that event, the plugin can request changes to any containers. A third one is a container resource update. So a plugin can respond to this by changing the updated parameters of the container and also extra updates to any other existing container in the system. So in addition to these, so these are all responses to container or pod lifecycle events. But there is also a third kind of change that plugins can request, and these are unsolicited changes. So you might have a metrics collection loop or some other monitoring loop which is somehow collecting data from the system and out of that or based on that, the plugin can decide that, okay, now it's a good time to somehow reparameterize the containers. And then without any event coming in, you can say that now I want to go ahead and do these changes. And these are similar to a stop. So basically you can modify resources of any existing containers. So a few words about plugin deployment. So, so there are two ways how an NRI plugin can be deployed. So one is tightly coupling it with the lifecycle of the runtime, although we told that they are not tightly coupled, but there is a way how you can tightly couple it. So in this mode, basically you deploy it as a worker node distro component using usually package management. And in this case, it is automatically discovered and activated by the runtime when it starts up and getting shut down when the runtime goes away. And there is another, which is loose coupling, and that has a much more cloud-native look and feel. So in this case, you are deploying it as a daemon set, so it will run on all your worker nodes, and this has the additional benefit that, so for instance, you can fetch configuration for the plugin as a custom resource. You have access to extra data through the API server, so everything that we know and learn to love about Kubernetes deployment sets.
So a few words about the state of the project. As I already mentioned, the project was started like almost 5 years ago, but real like big changes and current shape of the project was done like in the end of 2022. Like the 23 and 24, we saw what the project got started to adopted by different cloud providers. So we have like bunch of Chinese companies. Google started to look at it. Red Hat had some use cases and so on. So practically, like the last year October milestone was one of the like biggest stability point of view releases for NRI API. We got it into the shape what it can be enabled by default in the both of the common runtimes. So it's like containerd 2.0 shipping it is default enabled. Same with CRI-O a bit earlier than that. People are contributing, so we have like almost 70 forks of repository. Half of them actually contributed something back, which is I think it's quite a good sign. We have like new feature requests coming. Luckily, like less bugs coming, but we are working on it. And let's look more deeper in the features.
So as Sasha told, so ever since NRI is on by default in both containerd and CRI-O, we have seen a uptake basically in community involvement, community contributions, especially in contributions. So just to name a few, so for instance, we received from Red Hat contribution for WASP plugin support. So in addition to a native binary, you can also write your plugin or compile your plugin into a WASP binary with some limitations, but mostly comparable to normal native binary plugins. We received the network interface injector plugin from Google, and also add limit support from Google. So most of the work that we currently do for NRI are revolving around trying to reach a API stable 1.0 version. So I think we secretly hope that it will be by the end of the year, but cannot really predict that. Yeah, it's not really a promise. So what we have been doing for this 1.0 release, so we have been adding missing controls for existing OCI spec features that we haven't supported so far. Then controls for new OCI spec features, which have been recently added or being added right now. We have also been addressing some missing bits in the protocol, which will allow us to merge long-pending PRs about more controversial contributions. So these two most controversial ones that I talk about are both, by the way, contributed by Netflix. So Tycho Anderson from Netflix, and they are both security related. So one is about container Linux namespace adjustment. So you would be able to basically change in which Linux namespaces your container is running. And the other is about adjusting the seccomp filters that is getting applied to a container. So these both, although they were positively received by the community, but and the larger community, but they were raising a few eyebrows that, okay, maybe what do I do if I don't want this to be enabled in my cluster? So it's either on or off. And this is one of the sort of longest requested feature by some of the container maintainers, that it would be nice if we would have more fine-grained control and there would be some mechanism in NRI that selectively we could lock down some of the features. But during the discussion of this selective lockdown, actually it has been improved a little bit. So the current idea and what we are actually adding, and there is a PR open about it, is adding reliable plugin identification and then tying different sets of features to different identities. So basically you will be able to trust some of your, so for instance, you will be able to trust your own plugins fully and say that my plugin with this identity can do whatever. And then some other plugins which are not yours, they could have some of the features enabled that you do not consider so dangerous in the cluster, but you can lock down those, for instance, seccomp filter adjustment, which you might consider that, okay, if I allow anybody to do this, that's a little bit bad for them. Or it's not necessarily bad, but not something that I would trust people to do in my cluster. And basically NRI is about your cluster, your rules, so you are supposed to be able to do these things. And this pluggable validation and configurable restrictions is this mechanism that we are adding.
All right. So that was like the point of view on NRI from a developer's perspective and like from a plugin developer perspective. I would like to switch the gears and talk about the things like what is NRI for you as a user of a cluster, or like what you can actually do in your needs. First of all, I would like to point what like even the NRI API part of repository, it contains like few of example plugins. There is another repository on the GitHub under containers initiative, well, part of also CNCF, where we are collecting the community maintained set of plugins, and those like more like production quality, I would say, with more functionality, and whereas like having more separation on the topics what we are trying to do. Today I want to highlight like mostly the plugins which is related for the CPU and memory activities, but I will also say a few words about others. It's actively developed project, so we had a release, well, just a few weeks ago. It's available on Artifact Hub, so if you want to try, it's easily Helm install available, just few comments away from your cluster. So, plugins, what we have available. The first plugin I want to showcase is so-called topology-aware policy. This is the policy for CPU and memory allocation for the workloads. So if you're familiar with Kubernetes internal herd of managers like CPU manager, topology manager, memory manager, device manager, and so on, this is one thing which does that better. So it handles not only guaranteed containers, but all other PodQoS classes. It does it transparently, so you don't need to worry about it. Majority of the things it does without any configuration. If you're advanced user, you can have something, but it knows about the modern hardware, including like, well, some of the generations of upcoming hardware. It knows about things what like normal kubelet doesn't know. For example, like the storage devices. Like if you have NVMe devices, you can get the performance also out of those. By default, you install it, it will try to do the magic. If it doesn't help, then we have more advanced features. One of these is called balloon policy. And with balloons, we have, like, it incorporates most of the code, most of the logic from topology-aware, so it knows about the hardware, it knows how to optimize, but it gives you a flexible controls of how you are splitting your system, how you are separating the applications. And we have several use cases depending on what you're looking for. Like Simple example, you have like databases, consumes a lot of disk, consumes a lot of I/O, CPU, and so on. You have other like supporting containers, like your health probes, you have loggers, and so on. So if a database consuming too much of the resources, those support containers might go away and might cause the problems for like overall node stability, consider it to be unhealthy. So we give you a control to separate them, to limit the burst stability, limit like how much noise those groups of workloads can contribute to each other. But it's not only about that, it's also about the hardware. So each of the balloon, each of the pre-allocated CPU set or memory set for the group of workloads can be individually controlled. So we provide you ways to control the CPU frequency, to control the sleep states and so on. Another good example is, let's say, like you have a storage, and you have a storage which should prevent CPU going to the sleep mode, because like waking up from CPU takes like few microseconds. You can define what like my storage, like SPDK or kind of workloads like Ceph or whatever you are using, is high priority workload, always awake, always keeping the CPUs awakened. But when all of your like smaller part of workloads on the same node can save some of the power and eventually like save some of the money from your data center. Similarly, it can be integrated with our external systems. So, for example, like if you are predicting what like you will not going to be having a big workload during the night, you can like minimize the frequencies. The system will be still working, but the performance of services will be less and less consumption of the power. Another use case for balloons policy is actually coming from the modern world of AI workloads. So if you know, like most of our AI workloads running on GPUs, and yes, it's expensive and maybe not always economically reasonable to do the things on GPU. Some smaller models or some activities you can do on the CPU. And when you are doing that on CPU, the AI workloads have two particular, I would say, like bottlenecks. One bottleneck is memory bandwidth, and second is performance of arithmetical units on CPUs. So if you try to run multiple instances of AI workloads, most probably you will see contention between the hyperthreads on the same machine, or just, well, contention just because the same cores I use it for similar workloads. We, as part of the IPA project, like Open Platform for Enterprise AI, we provided some of the examples how this can be configured to run more efficiently, like how efficiently to utilize the memory bandwidth, how to split it between multiple workloads, how to maximize outcome of your hardware. If you're interested in that particular topic, here is the link and it will be available in the presentation. Speaking of memory, one more example of how NRI plugins can work. So you know the standard setup. What like you have like swap, you have normal memory, you have disk. Currently in Kubernetes, it's almost like non-configurable. Like you either have swap completely off, or you have swap on and it's applied for all the node, which is not good. We created, one of the projects what our team is maintaining is called memtrd, so like different types of memory. It started with specific hardwares, like high bandwidth memory or CXL attached memory, but it can also work for normal memory, like let's say balancing between the several NUMA nodes on the same system. Same thing applies to customizable swap out of the pages. So you can define what like these programs or this subset of workloads will be the first to be swapped out. And it's fully configurable, and you can say what like these workloads should not be touched at all in any scenarios. Again, like this is the tool which allows you to do like a lot of modifications to the container, and like you might have different rules how to do it. Speaking of different rules, devices. One good example of NVIDIA GPUs. Yes, currently in DRA, there is a feature which allows you to give access to the management containers, where the allocation for the all GPUs are not really happening, but you have some system daemon which has access to all the devices to get the statistics out of it. And it took, well, some time to implement in upstream. But as a stopgap solution, our colleagues from NVIDIA, they implemented the custom NRI plugin, which allows you to, based on specific criteria, to inject access to all of the GPUs. So again, like completely transparent to the Kubernetes access to the internal properties of the devices. Then we have another example, again specific to the devices. If you might know, in telco world, we are quite picky about like how a system should be set up and how things should be working. And sometimes it goes to like nifty details, like what on this CPU core, when I'm processing the packets, I don't want this CPU to be serving interrupts for, let's say, other hardware, like disk drives, anything else. So what we're seeing is like one of the companies created the plugin which was actually doing exactly that. So like as soon as the workload started and as soon as we see what like those CPU cores will be used for critical workload, let's remove interrupt processing from all of those cores. Again, your cluster, your rules. Our people doing more interesting even things. So like in Google, we saw what we're applying the U limits or R limits. So practically like how many files your container can be opened by default, like how many processes can be inside your container by default, and so on. We have some custom hardware which is not about the DRA, which is not about the device plugins, but we still want to do things. There are people who are doing with different kind of telemetries and injecting eBPF tracers on the container start. So, for example, of this inspector gadget. We have Chinese companies like Alliance of Chinese companies, which is working on this coordinator project. Again, it's similar to the resource policies for CPU and memory, what I showed before, but, well, more, I would say, like product style, what Alibaba and several other companies are working. And, well, any kind of debug, any kind of introspection for your workload, it can be done. So, as I said, your cluster, your rules. The question is what your plugin, what your opinion will be. And one request from us is actually try it. If you have some ideas, if you have some problems, or if you have some new use cases, please share with us. We are really like welcome community from, well, like Red Hat, IBM, Google, us, Intel, NVIDIA. So we are really interested to see and hear what kind of problems you are trying to solve, how you optimize your clusters, and what kind of opinions you have on it. And with that, that's it. So we can have some questions if we have a few minutes. It works on virtual. It works. Okay. So the question is like, does it work on bare metal or it works on virtualized? It works on virtualized. Of course, there are some features which might be limited. So, for example, like what I showed about the CPU frequency control, like obviously it will not work on virtualized. But for example, like tiered memory, like swapping out of the pages of low-level applications, or just like grouping the application and giving the different priorities to them. There is nothing specific on bare metal for that. Like you just use the standard Linux control interfaces to get that.
I think one limitation is that so if your hypervisor is set up so it's wired so that there is a one-to-one mapping between the virtual CPU presence and some physical core, then there is a good chance that you can use this and it will do something reasonable. If it's juggling those dynamically, then whatever this is seeing has nothing to do with reality, and there is a great chance that random things will come out.
Well, luckily nowadays, like the big CSPs are not doing with juggling anymore. because the hardware is evolving, like we have more cores, we have more resources available, so we are not that restricted. But yeah, most of the things you should be able to do. And we verified what the NRI plugins can be installed like in major clouds like Google, Amazon, Azure. You can, like all of them already migrated to recent versions of Containerd or CRI-O, so it should be usable.
Is it safe to summarize that NRI is kind of like an interface and a framework, just like admission controllers, but on a quite much lower level in a sense? But, you know, conceptually, at least I got the impression that it's pretty much doing the same things.
Yeah, so the question is, can the NRI be considered as admission controller on the low level? Answer is yes. So practically, it's a mutating hook in Kubernetes terms. Practically, it's mutating the OCI spec of the container. So the kubelet, when it talks to the runtime, it doesn't talk with OCI spec. It talks with abstraction. I want to run the container. This is the mount points which going to be. This is the environment variables which is going to be. And few parameters. And like the list is like that. But if you look at the OCI spec, the list of parameters is like that. And this list of parameters is maintained as part of the CRI-O containerd. So what NRI gives you is practically the way to modify this huge list of the parameters. Well, not everything, as Krisztian mentioned. What like there are some controversial things like what community is not really eager to allow us to do, like the security-related things, unless we implement some mechanism of controlling it. But pretty much like everything what is related to the resources, everything what is about priorities, yes, you can do it.
And if something is there which we would like to have, but we don't, then if you let us know, then we are interested in taking a look at it, whether we could have it.
Yeah, we did the sweep through the spec saying like, okay, well, this will be interesting to people. Let's add it to NRI protocol. This is not usable, or well, it might have security implication. Let's not do it right now. Let's see if somebody from the field will ask for it.
Generic purpose, like we have like Rego language now for admission policies and things like that. So people wouldn't have to always write their own protocol implementations and all the nasty low-level things.
So the question was if it was a discussion about we're implementing some of like domain state languages to express the rules. The answer is yes and no. Where people are scared about the custom languages. And this is actually part of this thing what Krisztian mentioned about the validation plugin or validation variants. So the agreement was what like let the people to write the plugins in the languages they like. So most of the plugins are written in Go. There is a Rust implementation of NRI protocol, so you can do it in Rust. WASM is coming, so you have plenty of choices. Like if you want your custom language or custom logic, feel free to use it. But like the low-level protocol will be something what we can do extensively.
And one thing that NRI provides that if you have some ideas, that hey, this is the subset of my custom language I would like to cover, and if the necessary controls are already in NRI, then you can try to roll an NRI plugin, and because NRI is also good for prototyping. So you want to contribute something, let's say to the CPU manager, memory manager, but that's first you would like to really know whether it's worth the effort, because contributing there is not that easy. So that takes time. So then you can dry run it. Hey, let me try. I implement it. Let me try on my workloads. Ooh, it helps a lot. Okay, maybe I will try to go through the effort and I try to upstream it there. If not, if you cannot, then anyway you have done the implementation, then you can plug it into your cluster, and then it's a win-win.
The example of that was like about a year ago when Google tried to implement the C Groups version 2 memory high control. And they had a great idea what it will help. We spent, I don't know, like how many release cycles to actually get that thing into upstream Kubernetes, and when we realized that what actually kernel behave a bit differently compared to what we expected. So something what we can do easily in NRI plugin, just like set that value and see how it behaves.
Other good example is that I should not tell my boss was when AMD was thinking about upstreaming cluster level. So basically CPU clustered CPU allocation. So that was first tested out as an NRI feature. And once they saw that, okay, this is great, then they upstreamed it into the, so that you can do it also without NRI. But this is just between you and me, not my boss.
Yeah, and I think we run out of time. Thank you so much.